Conversely to the previous to last day, where most of the presentation were dedicated to the numerical modeling, my talk today is more experimental work. Okay, we need experimental, of course, to validate the numerical modeling. So my talk is about the effect of fines on the mechanical behavior of kernel material. We focused our research on investigating at this point on the onset of instability and on the critical state line of silty sand. And this is with respect to the liquefaction phenomenon. So the present statute is that we well know the behavior of clean sand, especially at macroscopic scale. However, the existing material in nature are often made of fine particles and coarse grain. Such of this material could also be found in hydraulic structure, particularly in dike. Why I introduced the hydraulic structure? It is just because such structure are often submitted to important successive floods, which could wash out the fine particles from the soil by flow water, leaving behind coarse grain skeleton, which could become loose. Then, when this process arrives, this process is called the diffusion. When this process occurs, we have a change of the soil microstructure characteristic will lead to the change of the mechanical properties of soil resistance. Then this hydraulic structure could fail by the liquefaction process. I show you here a well-documented example, which is the failure of Dyszow Dam in Poland. The back analysis of this failure has shown that the sand was very loose and has a very low relative density, which was not explained by the initial state at construction. Just before the failure, settlement of 10 centimeters of the embankment was observed, and the initiation of the sliding was due to the vibration caused by passing truck. This back analysis showed that, or concluded that, this failure was due to an erosion process which took place during 15 years. Okay? So, when we deal with material search, the silty sand, the used approaches is different as the one we used when studying the clean sand. In fact, in this case, we could have three types of structure. The type 1, in which the fine fits in the void and doesn't participate to the chain force. In these cases, the main shear resistance is supported by the sand skeleton. We have a second type in which the fine fits the void and try to be situated between the coarse grain. So they start then to participate to the forces and to participate to the shear resistance of the soil. They start to be active. And we have the third cases where the fine occupies all the void and have equal role as the coarse grain. So in our study we are just interested by this part, which is characterized by a fine content which is below of the threshold fine content. This threshold fine content represent the amount of fine above which the behavior can change the tendency. We go from silty sand structure to sandy silt structure. Okay? So to study this type of structure, it was the use of the global void ratio appears inappropriate. So other density parameters were introduced, such the intergrain void ratio by Mitchell, where he considered that all the fine are non-active and do not contribute to the mechanical shear strength of soil. This is related to the case 1. We have also the second parameters, which is the equivalent intergrain void ratio introduced by Tevaregan, and in which we consider active fines and inactive fines. So to resume these three parameters, we have in the global void ratio the fine as considered as solid. In the intergrain void ratio, the fine are considered as void, and then in the equivalent void ratio, the fine are divided in two parts. One part which is considered as the void, and second one which is considered as a solid. To calculate this equivalent void ratio, we have to determine the parameter B, which represents the fraction of the active fines. And this is the challenge in this work. So I move now to the case study, which concerns the mechanical behavior of silty sand, which was taken from Camargue dike. This silty sand is constituted with fine and uniform sand and with non-plastic fines, the grain as C-bangular to C-bounded. Here are the grain size distribution of the pure fine, the clean sand, and different mixture with fine content varying from 5% to 20%, which are used in our experimental work. The experimental device is just this servo flow control triaxial cell, and this small cell which permits us to measure the variation, the volume variation of the mixture, and also the compressibility of these samples. So before to perform any mechanical test, we first characterized our soil in terms of the void ratio as we are working with silty sand. We found that the void ratio, the maximum and the minimum void ratio, varies with the variation of the fine content. You see here that the evolution of the minimum void ratio is as follows. It decreases until it reaches until a certain amount of fine content, which is about 20%, and then start to increase. As I said before, this value corresponds to the threshold, to the fine content of Camargue silty sand. The compressibility test we performed on the different samples confirmed this threshold. So, in terms of the results concerning the mechanical behavior, I show here only the results obtained under compression test performed on two series of samples. The first series were prepared at constant global void ratio, and the second series were performed at constant intergrain void ratio. And we used different fine content varying from 5 to 20%. Here you could see that almost of the sample, tested sample exhibits liquefaction flow behavior as presented yesterday by Felix and Guillaume, and which is characterized by this peak resistance and this rapid decreases of the shear resistance. Here we could see that the shear resistance at the steady state or the critical state, which is represented here, increases as the fine content increase. Concerning the evaluation of the shear resistance at the peak strength, we presented these parameters versus the post-consolidation global void ratio and the post-consolidation intergrain void ratio. We see here that the shear resistance at the peak decreases with the fine content. Conversely here, the shear resistance at the peak decreases until 5% of fine content and then start to increase. This point is very important because usually in the literature it was shown that below the threshold fine content, the fines doesn't play any role and are inactive. But this research shows that even below the fine content here, which is 20%, our fines start to participate to the chain forces. The other point here is that when we are dealing with diffusion, the more appropriate parameter to use is the intergrain void ratio, because when the diffusion happens, we have the washout of the fine particles, but the sand skeleton remains constant. Then we have to use the intergrain void ratio. So usually when we analyze the initiation of the instability, we use the concept of the instability line introduced by Ladd. This instability line is a line which leaves the peak strength of different sample shared under different condition but having the same initial density. However, if we look at more precisely the evolution of the stress ratio at the instability, the eta instability, we could see that this eta varies as the confining pressure varies. So we analyze our data by using another concept, which is the concept of the instability curve. This concept is based on the state parameters psi0 introduced by B. So for our case, we replace this psi0 by psi instability, and we calculate it by using the void ratio at the instability minus the void ratio at critical state corresponding to P dash equal to P dash instability. Then when we plot our eta instability versus the psi instability, we see that all our data merge on the same curve. This data concern the clean sand. We did the same analysis for the sand with fine, and in this case we also found that this curve is valid for the mixture, and this has very big importance in the stability analysis, as we could see later. In terms of the analysis of critical state line, we reported here all the point obtained at steady state for the several series of tests. We see clearly here that for each fine content, we have one critical state line, which is different from one to the other, depending on the fine content. We could see also that the shear resistance in this case at critical state line decreases as the fine content increases. This is coherent when we use the global void ratio, because in this case when we prepare the sample and when we increase the amount of fine content, we decrease the amount of sand scale, the sand grain, which means that when we increase the fines, the void ratio of sand decreases. As below the fine content, the threshold fine content, the main barrier is governed by the sand skeleton, then here we have a decrease of the shear resistance. Okay? So now when we present this value, this critical state, in terms of intergrain void ratio, we have an inverted tendency. In this case, the shear resistance increases with the fine content, and also it is consistent because the sand skeleton here is constant, and just to add some amount of fine. what I presented here is just the threshold void ratio, which is characterized by the intersection of this line with the y-axis. And we could see clearly that this threshold void ratio decreases with the fine content in this case, and it will be the inverse in the other one. Okay, now to try to determine this parameter B, which represents the active fines and which is the main parameter in this research, we realized that in the past years, several researchers used determine these parameters arbitrarily just to fit their experimental data. But Rahman in 2008 proposed this expression for B, which varies with fine content. This expression contains the fine content, the threshold fine content, and K, which is related to the size ratio of D50 of the fine particles over D10 of the coarse fine particles. However, this formula is physically ambiguous and doesn't take into account the effect of density parameters, which is the main parameters which govern the mechanical behavior of soil. So based on this, we proposed the new approaches to estimate the parameter B. The basic idea of these approaches is that fine is active when its coordination number is greater than 3. And the physical basis of these new approaches is that the distribution of fine particles coordination number can be represented by the normal distribution curve, I mean the quotient distribution, which has the probability density function and the cumulative distribution function as follows. So the fraction of inactive fines, 1 minus B, is equal to the probability to the fine particle to have coordination number greater than 4. Then 1 minus B can be calculated by this integral. So then we obtain this expression of B as follows, where CS is the mean coordination number of small particles, and sigma is the standard deviation. The calculation of sigma was done by using the approximate relationship provided by ODA, and which is equal to 2 CS. To calculate then the coordination mean number of the small particles, we defined three types of mean coordination number. The global one, C, the individuals one, CL to large particles, CS to small particles, and the partials one, CLL large, CLS, CSL, and CSS. This gives us then this system of equation. To resolve this system of equation, we assumed that our mixture is homogeneous, and then we applied the relation given by Fields, which is C equal 12 to 1 over the void ratio, to the sand in order to calculate CLL, and to the fines to calculate CSS. Thereafter, we make the hypothesis that the ratio of the contact number of a grain with coarse grain and fine grains is proportional to the ratio to the total area, so we could calculate the CSS over CSL. Then we obtain this expression of the mean coordination number of small particles with X equal D50 in this time of the coarse grain over D50 of small grain. To check the validation of this formula, we calibrated with the experimental data provided by Pinson, and we obtained this expression of CSS. So we introduced these two parameters, then sigma and CS, on our expression of B, and we obtain this last formulation of B. Here you could see that we take in account the fine content, we take in account the X, then size ratio of the particles, and we take into account the void ratio, which is not done in Raman formula. So we use then this B to recalculate our void ratio at critical state and at the initiation of the instability. You see in the plot representing the derivative stress at the peak versus the equivalent void ratio, that all our points at the instability merge to the same curve. We have the same constatation concerning the critical state line. So we could see that the equivalent void ratio presents good correlation with the resistance at the instability and critical state. It represents the relevant density parameters in the analysis of the behavior of silty sand, especially in the critical state framework. So to check the validity of these new parameters, we did back analysis of several results presented in the literature, and you could see clearly that this new formula is valid, as it permits to merge all the data on the same line. We did the same for other results in the literature. So from here, and to conclude, I just want to present you this simplified framework, the methodology to use this simplified framework. So to predict the steady state line of sand with different fine content, we have first to determine the steady state line of the clean sand, which is easy to perform in the lab, and then for any value of M&MoCS at steady state, we calculate its corresponding void ratio. Here, the void ratio is equal to the equivalent void ratio if we base on the initial approach presented. So, from the data set of the equivalent void ratio, we calculate the corresponding global void ratio E of sand with fine by first calculating the parameter B as presented previously, and secondly by calculate the void ratio E from the equation 2. Then by repeating the step 1 and the step 2, we could generate, for any value of M&MoCS, we could generate complete steady state line for sand with different fine content. Then we don't need to perform several tests with different soil with different fine content. If we have just a critical state line of clean sand, and if we know the fine content of the soil, we can generate different steady state. And this is nice result for the engineering society, I think. Thank you for your attention.
Time for one question. How do you mix homogeneous matter, your mixture of fine and sand?
Yeah, we did it first on dry condition, and just by washing we try to be more homogeneous, and then we modify the soil because we use the moist dumping.
It's the water in dry condition.
Yes, yes. We checked the homogeneity by repeatability test, which were good, not by visualization yet.